Good morning all. Here is a trainer for the microprocessor unit MC6809, the Motorola 6809. Now I'm going to use this trainer to test this SRAM down here, and its part number is MK6118N. It's 1K by 8 bits of SRAM made by MOSTEC. Now, that device is obsolete and I want to know if it's good or bad. So I have it breadboarded down here, and the address, control, and the data bus are connected to the SRAM. And over here I have a 74LS00 for timing, the right timing of this device, the read and write timing of this device. And I'll show you my drawings of this little circuit right here at the end of the video. And I'll also discuss the program that I'm going to enter to test that SRAM. But what my program is going to do, it's going to enter hex 55 into all its memory addresses. 55 is 0101 0101, and then it's going to compare all addresses back to all the memory addresses back to that value of hex 55. Then I'm going to enter hex AA, which is 1010 1010 into all memory addresses, and then compare back all those memory address data of AA. And if all is correct, then I'll have an address called pass-fail memory, and we'll go look at that. And if it contains 000 hex, then the memory passed. But if the memory failed, it will contain FF, all ones. Let me enter the code. We'll power it up first. There we go. It says C.I.E.6U9 dash, and then these segments over here alternating. Now here, let me put this out here in front real quick. This is the code that I'm going to enter. Here are labels, opcode, and operands. And here is the assembled code right here in hex. This is what I'm going to enter. Starting at address 0000. That's this piece of RAM up here where we enter our programs. That RAM is at address 0. So let's press the address data button. Here's address 000, and here's the data contained in that address. We can change that. Wherever you see these decimal points right here, that means that that portion is editable. We could change it. I must be hungry. I'm thinking food. So here we go. Our first byte is 8E. Press the plus key. That advances the address to 1. And we're going to enter A000. Now don't worry about what all is going on right here. At the end of the video, I'll go over this program. Right now I'm just entering it into memory so we can run it. There, our program has been entered. That's the complete program to test that SRAM. Now when I come back, I'm going to take a little bit of a break. When I come back, we'll run that program and we'll test that RAM. We'll also set up the RAM to fail. I'll disconnect VCC from +5 volts. And that'll unpower that RAM. And it'll fail, of course, when we try to run the program. See you in a little bit. All right, I'm back. Okay, let's continue. Now, we have to set a breakpoint so that when we run the program, it doesn't shoot through the end and lock up the processor. We have to tell the program, the computer, where we want to stop. So here's on the number 2, shift, set break. Push the shift key, and here we can enter a breakpoint address. Now, at address 4B, I entered a no-op. That's operand 12, opcode 12, sorry. So, we want to set our breakpoint at 4B. There we go. We're ready. Let's take a look real quick and set our address to 0. There's our first opcode right there, 8E. Now we want to run, so we're going to hit go. We have to set an address for go, and here we are at the beginning of our program. Hit go again. Come on. Now I got to remember how to do this. Oh, yeah, okay. Hit the plus. And here we stopped at address 4B. Did you see how fast that was? We ran through the program from address 0000 to 004B. There's the no op code right there. Now we want to go to address 100. That's our pass-fail memory, and see what value is in that memory. If it's 00, the RAM passed. If it's FF, the RAM failed. So let's go shift address 0100, and look at that. At address 0100, that's our pass-fail memory, we have 00. Now I'm going to disconnect the 5 volts from the SRAM. Now the SRAM is not powered up. We want to hit go, shift go, and we're going to enter 00000 and hit the plus key. Is it the plus key? I can't never remember. Okay, yes. Hit the plus key. Now we're at address 004B. That's the end of the program. There's our opcode no op, hex 12. Now we want to go to address 0100 and see what value is in there. Hit shift address, and look at this. We have FF. That failed. That SRAM failed because we disconnected the 5 volts. Now let's hook the 5 volts back up and run the program again and see what we have here. Hit go. Enter 0000, the beginning of our program, in SRAM up here. Hit the plus key. We're at the end of the program again. And look, at address 0100, we have 00 again. That's the pass indication, since we powered up that SRAM again. Isn't that neat? How you can use something like this to test old RAM like that. All right. I like that. That is really neat. Now, when I get to the house, I'll show you the schematics of connecting your trainer if you have one, I imagine you could find these on eBay. I got this one from college. And I'll show you the connections to test your SRAM, part number MK6118N, manufactured by MOSTEC. And I'll show you the code that we ran to test that SRAM. Takes a little while to type in, but it's not impossible. You saw us do it. All right, folks. Thank you very much for watching us test that SRAM. That was a lot of fun, wasn't it? All right. Let's go find something else to work on. Have a good day, folks. Have a good day. And we'll see you next time. Hello all. Here we are at the house. And we're going to look at how to connect that MC6809 trainer to the SRAM, part number MK6118N-2, manufactured by MOSTEC. Now the processor, the 6809, emits timing signals on E and Q. There's pins of that processor called E and Q, and they allow the proper timing of external devices to that processor. Now here, there's a data bus enable bar on the trainer, and I connect the processor's E pin with the jumper wire to data bus enable bar. When E is low, the data bus on that trainer is enabled. Now here, this is the connections of the trainer. Here's the connections with jumper wire to the SRAM. Address 0 through 9 on the trainer are connected to address 0 through 9 on the SRAM. A0 being on 8, pin 8, A1 on pin 7, A2 on pin 6, A3 on pin 5, A4 on pin 4, A5 on pin 3, A6 on pin 2, A7 on pin 1, A8 on pin 23, and address 9 on pin 22. Let's take a look at the rest of the circuit down here. We're going to look at the data bus and control. Alright, now here's the data bus. We have D0 to D7 on the trainer, and with jumper wires I have it connected to the data bus on the SRAM. Here's D0 connects to pin 9, D1 connects to pin 10, D2 connects to pin 11, D3 to 13, D4 to 14, D5 to 15, D6 to 16, and D7 to 17 on the SRAM. Well, how'd y'all do anything with 8 bits? Ain't enough. Well, imagine way back when we did all kinds of things with no bits. So there you go. There's 4-bit processors out there. There's even a Motorola monobit processor. Have y'all ever heard of that? 1 bit. Okay, let's go look at the control. Alright. Now here, from the processor, we had the read/write bar connected to pin 21, the write enable bar, through jumper wire. Now here is address A 8000 bar. That's the address on this strip terminal right here. And down here we have Q. Q is much like enable. It's out of phase with enable, but I use it in conjunction with address A000 bar to chip enable that static RAM. So when A000 bar goes low, when I'm addressing that IC, we have a low here and then a high here on pin 3 going into pin 4 of this next NAND gate. When you tie two inputs of a NAND gate together, you've created an inverter. So here we have a low, and then here we have a high. Now when Q goes high, Q is a processor function. That's a pin on the 6809 used in timing external devices. When Q goes high, we have a high on pin 5, and we have a high on pin 4, and we have a low. This is a NAND gate. A high and a high makes a low. That SRAM is chip enabled. We have CE bar, chip enable bar. Isn't that amazing? Now, in a little bit, we'll discuss the program to test that MK6118N SRAM with that 6809 trainer. Here, I was able to disconnect and make that SRAM fail by removing 5 volts from pin 24 VCC. Pin 12 VSS, that's ground. Here we have an output enable on pin 20. Now the MK6118N 19 is a no connect, but I've used this same function to test other obsolete RAM, and the other obsolete RAM had an L bar on pin 19, but the MK6118N-2 pin 19 is a no connect. Isn't that amazing? How you can take something from the 80s, 90s into the 21st century like this. So, don't throw nothing away. Keep all your old computers, your old laptops, keep all your old electronics. No, folks, don't throw nothing away, because you'll be saying, why did I throw that away? I could have used that. All right, folks. Enjoy your time on this side of the dirt. In a little bit, we'll talk about the code. Here's the assembler code to test the SRAM. This is the complete listing, and in the next few photographs, we'll get closer so that y'all can see what's going on. I've got the next few photographs broken down into sections, and we're going to talk about setting up the equates, the beginning of memory where this program will reside, and setting up the index register, loading the A register with the value 55, storing that value in SRAM, then comparing that value 55 back to the compared value, then loading AA into RAM, comparing AA back to that value of AA, and ending the program. And if all is well, we jump to memory test end, which is at address 4B where we have the value of no op. If the RAM fails, we load the pass-fail memory with the value of FF. Here we set the equates. This is a command that the compiler recognizes, EQU. Here we have pass-fail memory located at address 100. Here is memory end high, and it is at address 101. Memory end low is at address 102. The memory end high and memory end low values that we're going to store at these two memory locations are the end address of that SRAM that we're testing. Org is another command that the compiler recognizes, and it states that the first address of our program that we typed into the trainer is at address 0000, address 0. Let's go to the next page. Here we load the X index register with the first address of the RAM that we're testing. This hashtag indicates that this is a number. The $sign indicates that this is a hexadecimal value, A000. That's where the breadboard resides that we place that RAM on. Next, we're going to load the A register with A4 and store that at memory end high. Next, we load the A register with 01 and store that at memory end low. So we have the beginning address in the index register X, and we have the ending address of our SRAM at A401. The actual ending address is at A400, but we want to go one beyond so that we, when we branch not equal, we will do so at the very last memory address, A400. Next, we have to clear the pass-fail memory, reset it to 00. So we load the A register with the number 00, and we store the A register at the pass-fail memory. Here we begin the test. We load the A register with the hexadecimal value of 55, that's 0101, 0101. Now we're going to store that value in all memory addresses of that SRAM under test. So here we have a label. It's called load loop 1, L loop 1. Store A, which has the value of 55, in the X index register, which is set to A000 right now. So we load 55, we store it at that address, and then this command increments by 1. And we're going to compare the X index register to A401 with this command right here, compare X A401. If it is equal, then we branch not equal down to here. But if it's not equal, we jump back up here and continue to the next address. And so now we would be at A001, and we store 55, which is in the A register, at A001. And we keep doing that until the compare X memory end high is equal. And when it is equal to A401, we branch over this right here. So when we're not equal, we loop back. when we're equal to the memory end high and memory end low, we jump over that and we go down here. Now we have to reset the X index register back to A000. And we load the A register with the value 55. And here's the compare loop. This is compare loop 1. So now we're at address A000 and we want to see if the value in that address of the SRAM under test is equal to 55. So we compare A, which has the value 55, to the address A000. And if that value in that RAM is 55, we jump over here and now we want to compare to see if we've made it to the end of the RAM under test at A401. But let's back up a little bit. If the value in the RAM is not equal to 55, we branch to the label mfail, memory fail, and at that point down there we'll load the pass fail memory with FF. So we haven't made it to A401 yet. Let's jump back up here, branch not equal to C loop, and we go up here and we test A001. This X plus increments. We compare and increment and compare and increment. So let's say we've passed, we've made it to A401. We jump over this branch not equal C loop 1. Now we're down here. Let's go to the next page. Here is where we're going to load the value AA into SRAM under test. That's 1010, 1010. First, we have to reset the X index register back to the beginning address A000. Then we load the A register with the value AA. Here again, this is just like before, we're going to store that value AA into memory. And we're going to continue to load AA into each successive memory location in that SRAM under test until compare X, memory end high, equals A401. That's memory end high and memory end low. Then we jump over here, we reset our address in the X index register to A000. We're at the beginning of the RAM again, the RAM under test. We load the A register with the value AA. That's 1010, 1010. And down here again, we're going to compare what's in the X index register memory, A000, and if it fails, like let's say the value at A000 in that RAM under test is not equal to AA, we jump down here to memory fail, and we load the A register with FF, store that in the pass fail memory location. If it compares, we go down here and make sure that we haven't reached the end yet, doing a compare X, that's the X index register. If it's not equal to A401, we jump back up here to C loop 2 and continue testing the RAM to make sure that it's equal to AA with this compare A, comma X plus. And when we do reach A401, we jump over this branch not equal C loop 2 down here to jump, memory test end. And that's right here. Memory test end is where we entered that no op at address 4B12. Well, there you go. Now I'll put all these photographs up at the end of the video, and you can go through each and analyze what we did. Now over here you see this column right here. This is the address in the trainer's RAM. That's not the RAM that we tested. This is the address in the trainer's RAM that starts at address 0000. And here's the opcodes and the operands that we typed into the trainer. So AE hex is load X. And here's A000, that's this, A000 right here. 86 is load A register with the value AA right here. Isn't that neat? Now let me go through this right here. We have this branch not equal load loop 2 that says if the compare X, memory end high and memory end low are not equal to A401, then we branch not equal to load loop 2, and that's back up here. Let's go over here to F9 and let's count backwards from F9 to FF. So we go F9, FA, FB, FC, FD, FE, FF. And that's where we are up here. Now when we're branching forward, let's find a jump ahead, okay? We're going to jump right here to memory end. We have 7E004B. 7E is this right here. 004B is down here. Now, what if we want to branch forward? That's a jump. Let's do a branch forward to memory fail. Memory fail label's down here. So we're branching forward if branch not equal M fail. And we have a 26, which is branch not equal, and we have an 8. So let's go 1, 2, 3, 4, 5, 6, 7, 8. Did I do that right? Oh, I got ahead of myself. Okay, 1, 2, 3, 4, 5, 6, 7, 8, and the program counter will be right here at 86, which is M fail label. Fascinating. That is fascinating. All right, everybody. I hope you enjoyed that video and you're doing well out there. Thank you very much for stopping by. We'll see you next time.